There's this invisible engine that's the absolute backbone of our modern world. It's in our homes, our industries, our transportation, just about everywhere. So how did we get here? How did we figure out how to turn electricity into motion? Okay, let's dive into this incredible story. Just think about it for a second. These things are on completely different scales, right? You've got a drone buzzing in the air, a blender whipping up a smoothie, and a massive bullet train screaming down the tracks. What could possibly connect them? Well, they all share one fundamental, world-changing piece of tech right at their core. That's right, it's the electric motor. It started out as this little scientific curiosity, and it evolved into the main way we turn electrical energy into useful physical motion. And it powers, well, pretty much everything. Now, to really get the story of the motor, we have to start with its power source, because for centuries, the only kind of electricity people knew about was not the kind you could build an engine with, not even close. So the ancient Greeks knew all about static electricity. That little shock you get when you touch a doorknob, but it's totally impractical. It just discharges in one big, uncontrollable spark. What inventors really needed was a steady, reliable flow of electricity, what we call a continuous current. And this is the breakthrough. In 1800, Alessandro Volta invents the very first battery, the voltaic pile. For the first time in history, scientists had a reliable source of continuous current. This invention literally changed everything. It opened the door for them to finally, systematically figure out the link between electricity and magnetism. So now we've got a steady flow of power. The next great challenge was staring everyone right in the face. How do you turn this invisible electric current into actual physical motion? And what's wild is just how fast things started moving once Volta's battery was out there. The breakthroughs came thick and fast. In 1820, Hans Christian Ørsted notices that an electric current can make a compass needle move. This was the first proof that electricity could create a magnetic force and cause movement, and it kicked off an absolute frenzy of experimentation. And just 1 year later, we get the big aha moment from the genius Michael Faraday. He builds this simple but brilliant device where a live wire just continuously spins around a magnet. Now, this wasn't a practical motor yet, but it was the conceptual birth of every single electric motor that would ever be built. He proved for the first time that continuous rotation was possible. Faraday himself called his creation a philosophical instrument. And that phrase just perfectly captures the gap between a scientific discovery and a useful machine. He'd proven the how, but this thing couldn't power anything. It was a marvel, a proof of concept, but it wasn't a workhorse. So that sets up the next great engineering problem, right? How do you take Faraday's amazing spinning wire and turn it into a machine that could actually do some work? Here was the core problem everyone was stuck on. An electromagnet is attracted to a regular magnet, right? So it'll spin to align with it, and then it'll just stop. It's locked in place. How do you give it another push to keep it going around and around? The solution was an absolute stroke of genius called the commutator, invented by William Sturgeon back in 1832. Think of it like this. It's a switch that flips the north and south poles of the electromagnet at the perfect moment. So just as it's about to lock into place, the commutator flips the current, which repels it and gives it another push in the same direction. It's this constant, perfectly timed flip that creates continuous, smooth rotation. And building on that amazing idea, an American blacksmith, Thomas Davenport, working with his wife Emily, created the first motor that was actually powerful enough to do real work. In 1834, they hooked their motor up to a small printing press and it ran. This was the moment the electric motor went from being a cool science fair project to a machine with world-changing potential. But, and this is a huge but, there was a massive problem: power. The zinc batteries you needed to run these motors were ridiculously expensive, not to mention huge and inefficient. I mean, why would anyone use a motor that cost a fortune to run when the powerful, cheap, and reliable steam engine already dominated all of industry? The electric motor just couldn't compete. But here's this fantastic little clue. A bit of foreshadowing. Those early inventors noticed something really strange. If you took one of their motors and just turned the axle by hand, it would actually generate an electric current. This discovery, that a motor could also be a generator, was the critical clue that would eventually solve the whole power problem and unlock the electric age. This brings us to the final, crucial phase of our story. This is where a series of brilliant engineering refinements, mostly happening in Germany, created the fundamental design for the modern motor that we still use to this day. So let's look at the key players here. First up, in 1856, Werner von Siemens creates the slotted armature. By cutting grooves into the spinning part and tucking the wires inside, he made the motor way more efficient and powerful. A huge leap. Then, in 1871, Zenobe Graham's ring armature solved a different problem. It got rid of the jerky, pulsating motion of earlier motors and created a much smoother, more continuous delivery of power. And finally, building on all of that, Friedrich von Hefner-Alteneck perfected the drum armature in 1875. This design was so robust, so effective, it became the blueprint for basically every modern DC motor that came after it. And that is just incredible to think about. The basic design that Hefner-Alteneck perfected in the 1870s, putting copper windings into slots on an iron core, that is still the absolute standard for how we build electric motors today. The blueprint was just that good. At the very same time, the science behind it all was being perfected too. The physicist James Clerk Maxwell, and later Oliver Heaviside, managed to boil down all the complicated laws of electricity and magnetism into just 4 beautiful, powerful equations. This gave engineers the perfect theoretical toolkit to understand exactly what they were building. So, by the late 19th century, the whole journey was complete. The science was understood, the engineering was perfected, and the problem of generating cheap power had been solved. The humble electric motor, born from a little twitching compass needle, was finally ready to take over the world. All right, today we are diving into one of the most intense rivalries in the history of technology. This is a story about brilliant inventions, huge egos, and some serious corporate warfare. And it literally built the modern world that we live in. And that really is the question, isn't it? Because this wasn't just about the best idea winning out. Oh no. This was a story about a powerful giant, a brilliant underdog, and a PR war that got, well, shockingly dirty. And the outcome of this fight determined the kind of technology that's humming inside every single wall of your home right now. So to really get this fight, you gotta meet the reigning champion first. Back in the late 1800s, as the world was just starting to get lit up by electric light, one guy's system was the undisputed king. And that guy was Thomas Edison, the famous inventor. He'd set up the first ever investor-owned electric utility way back in 1882. And his system? It was all based on direct current, or DC. It was, quite simply, the only game in town. It was the standard, powering the very first light bulbs in big cities like New York. But here's the thing. Edison's DC system wasn't just about light bulbs. It had serious muscle, and that was thanks to a brilliant engineer named Frank Sprague. Sprague used to work for Edison, but he went off and created this absolutely revolutionary DC motor. I mean, just look at how fast his invention took over. In just 5 years, it went from being an idea at a new company to powering electric railways all over the world. It was tough, it was reliable, and it made DC the engine of industry. Even Edison himself had to admit it. He called Sprague's motor the only practical electric motor available. And that gave the DC system this massive, massive advantage. It didn't just have the lights, it had the power for industry. It really did seem unstoppable. But you know how it is. Every kingdom faces a challenger. And in this story, the challenger was a totally different kind of electricity, championed by an entrepreneur who saw DC's one single fatal flaw. And here it is. This is the core of the whole fight. DC power, for all its strength, had this huge weakness. It just couldn't travel very far. It lost so much energy over any real distance that you basically needed a power station on every city block. Now, alternating current, or AC, which was championed by a guy named George Westinghouse, had the exact opposite strength. It could be sent hundreds of miles, no problem. But it had the opposite problem, too. It didn't have a good, practical motor. So, with the battle lines drawn, you'd think this would turn into a war of innovation, right? A race to see who could invent the better system. But nope. Edison, terrified of losing his DC empire, decided he wasn't going to invent his way out of this. He was going to try to destroy his rival's reputation instead. So yeah, instead of trying to fix DC's big problem, Edison launched this just vicious propaganda campaign. His goal was simple and pretty sinister. Convince the public that his rival's technology, alternating current, was an absolute killer. And it got incredibly dark really fast. Edison and an associate held these public events where they would electrocute stray dogs and even old horses using AC power, all to create this spectacle of fear. And the whole campaign hit its peak when they secretly funded the development of the very first electric chair, and then made damn sure it used Westinghouse's AC power. They wanted to forever link that technology with death in everybody's mind. So while Edison was busy with his whole gruesome smear campaign, a truly brilliant mind was quietly solving AC's biggest problem. See, this war wasn't going to be won with fear tactics. It was going to be won with physics. And the man who held the key was Nikola Tesla. Tesla's big breakthrough was all based on this incredibly elegant concept, the rotating magnetic field. He figured out that if you use multiple AC currents and have them all pulsing just slightly out of sync with each other, you could create a magnetic field that spins all by itself inside the motor. No moving parts needed to create that rotation. This was the secret sauce that AC had been missing. And here's the genius of how it actually works. You've got the stationary outer part, the stator, and that's what makes the rotating magnetic field. That field then wirelessly, that's the key part, induces a current in the inner part, the rotor. Now the rotor has its own magnetic field and it just gets pulled along, basically chasing the first field around and around. It's such a simple, beautiful system. No brushes, no direct contacts, which meant no sparks and almost zero maintenance. It was rugged, it was efficient, and it was a total game changer. George Westinghouse saw it immediately. He knew this was the missing piece of the puzzle. He went right to Tesla's lab and bought the patents for a pretty hefty sum at the time. And just like that, he had the whole package. A system that could send power over huge distances and the perfect motor to actually use that power. Okay, so with Tesla's motor now in his arsenal, Westinghouse was finally ready to end this war and prove to the entire world which system was truly the best. And the victory came in two absolutely stunning public showcases. First, Westinghouse beat Edison's bid to light up the entire 1893 Chicago World's Fair. They created this dazzling city of light that just blew everyone's minds, all with AC power. And then they pulled off the ultimate feat. They harnessed the incredible power of Niagara Falls and sent that electricity all the way to Buffalo, New York. After that, there was no more debate. The war was over. AC had won. And the legacy of that win is just staggering. To this day, Tesla's design, that three-phase AC induction motor, using those out-of-sync currents we talked about, is still the most common industrial machine for anything over 1 kilowatt of power. Just think about that for a second. The very motor that won the war is still the workhorse of our entire modern world.
This simple little device sparked not just one, but two massive revolutions that changed everything. First, it completely remade the factory, and then it did the same thing to our homes. So how on earth did this quiet little box manage to reshape our entire world? Well, that's what we're going to dig into. All right, so here's our game plan. We're going to start our journey in the dark, pretty dangerous world of the old steam-powered factory. We'll see how the electric motor basically set it free, and then we're going to follow that same exact technology as it gets smaller and moves right into our houses. And trust me, that led to some really unexpected consequences. Okay, so to really get what a big deal this revolution was, we first have to understand the tyranny it overthrew. See, before electricity, the factory was a grim, brutal kind of place. It was a world totally held captive by one single, massive source of power. And this really gets to the heart of the problem. Just picture it. There's this one giant steam engine, probably chugging away in the basement, acting like a single beating heart for the entire building. And every single machine on every single floor was physically tied to this one engine. That connection created a total nightmare.
They called this the group drive system, and honestly, it was a nightmare of inefficiency and danger. Imagine looking up and seeing a whole forest of spinning steel shafts and miles of fast-moving leather belts crisscrossing overhead. That's how power got around. A ton of energy was just lost to friction. And get this, if that one main engine broke down, the entire factory went silent. Plus, because of all that weight and vibration, the buildings themselves had to be these heavy, dark, multi-story fortresses. It was inefficient, totally inflexible, and just incredibly dangerous.
And then, electricity shows up on the scene. But you know what? Its true power wasn't obvious at all, at least not at first. And this brings us to what we call the unit drive revolution, which, funny enough, started with a pretty big misunderstanding.
So, at first, the factory owners, they kind of missed the point completely. They just took out the giant steam engine and plopped in a giant electric motor, but they kept the same awful system of shafts and belts. But the real genius, the true revolution, wasn't about swapping out the factory's heart. It was the aha moment when they realized you could give every single machine its own tiny little heart, and that was the unit drive.
And this huge conceptual leap, this new way of thinking, it didn't just improve the factory. It totally reinvented it. It sparked a transformation that happened at a truly staggering speed.
I mean, what's really incredible is just how fast this all happened. Take a look at 1909. Only about a quarter of the power in manufacturing came from these new individual motors. Okay, not bad. But then, jump forward just 2 decades to 1929, that number absolutely skyrockets to over 77%. That is a breathtakingly fast takeover.
Yeah, in fact, by the time the 1920s wrapped up, a staggering 70% of all manufacturing in the US was running on electricity, and almost all of it was using this new unit drive system. The steam engine's long reign, yeah, that was officially over.
You can really see the night and day difference when you put them side by side. The old way, you had machines just clustered chaotically wherever they could connect to a power shaft. But with a unit drive, you could finally arrange them in a logical, sequential flow. This is what allowed for those light, airy, single-story factories that were so much safer and way more efficient. The entire logic of how you build a product had changed, right from the ground up. And here's the key takeaway. This new freedom of layout is what made the modern assembly line possible. I mean, think about Henry Ford's famous production lines. There's just no way they could have existed in that old world of steam engines and drive shafts. The electric motor literally unlocked a whole new era of mass production.
But hey, the revolution didn't just stop at the factory door. Oh no! While these giant motors were busy remaking industry, a much, much smaller hero was about to take that exact same revolutionary idea and bring it right into our homes.
And that hero was the fractional horsepower motor. The name kind of says it all, right? It's a motor with less than 1 horsepower. It was small, it was cheap, and it was reliable enough that you could build it directly into products for regular people. You know, everything from drink mixers to vacuum cleaners. And its rise was just swift. It was invented back in 1905, and by 1910, it was already being used in a commercial drink mixer, which basically kicked off the entire modern appliance industry. Fast forward to the 1920s, and as electricity started spreading to more and more houses, these tiny motors were powering a whole new wave of technology for the home. Which brings us to our final and maybe most complex chapter, the double-edged appliance. See, all these new machines, they were sold with a promise to liberate people, especially women, from the endless drudgery of housework. But the reality? Oh, the reality was a whole lot more complicated. And this is where the story gets really fascinating, I think. The promise, which advertisers pushed hard, was this future filled with leisure time. You know, kick your feet up while the machines do all the work. But the reality was something else entirely. These amazing new devices didn't actually get rid of the work, they just changed the very definition of what it meant to be clean. So here's how this weird paradox actually played out. Because a washing machine or a vacuum cleaner made the chore physically easier, society's standards for cleanliness just shot through the roof. All of a sudden, clothes you might have worn for a few days were now expected to be washed after every single use. You combine that with the fact that fewer families had hired domestic help, and what was the result? Well, for many middle-class women, they actually ended up doing more household labor, not less. Now, let's be clear about one thing. Despite this strange social paradox, the fractional motor was an undisputed, absolute economic game changer. There's no doubt about that. It created enormous new industries for consumer goods, it drove a massive wave of industrialization, and it laid the foundation for the modern household appliance market that we all know today.
You know, the electric motor is pretty much the invisible engine of our entire world. But it wasn't always the super reliable workhorse that it is today. We're going to pull back the curtain and see how 3 big forces, mass production, standardization, and yeah, the pressures of war, actually forged the modern electric motor. All right, to really get this, let's start with a problem that was seriously slowing down industrial growth almost 100 years ago. Just think about that frustration you feel with incompatible phone chargers. Now imagine that same problem, but scaled up to an entire factory floor. So the 1920s, they were roaring with powerful new electric motors. I mean, this was supposed to be the future, right? But for the people on the factory floor, it was a total logistical nightmare. The incredible promise of electrification was just getting stuck in this swamp of incompatibility. Think about this for a second. Your entire assembly line just grinds to a halt because one single motor burns out. You can't just go grab another one off the shelf. Oh no. You had to hunt down the exact proprietary model from the company that originally made it. It was a huge bottleneck, costing so much time and money, and it was holding back the whole industrial economy. So to break this gridlock, industry leaders knew they had to do something pretty radical. They had to get together and agree on a set of rules. It was time, really, to create a universal language just for motors. So NEMA's goal was, on the surface, pretty simple. But in reality, it was absolutely revolutionary. The idea was to create this universal language for motors so that no matter who made it, a motor with the same NEMA frame number would be a perfect drop-in replacement. This wasn't just about convenience. This was about unleashing economic velocity. And these standards weren't just set in stone and then forgotten. As material science got better, we're talking better plastics, better synthetic insulation, engineers suddenly realized they could pack way more power into smaller and smaller packages. So NEMA kept up, introducing the more compact U-frame and then later the T-frame, which is still the absolute workhorse in North America today. So that number you see stamped on a motor, it's not random at all. It's a super precise geometric language. A 145T motor will always have a shaft that's exactly 3.5 inches from its base. It is a guarantee of a perfect fit, every single time. It's basically the code that makes modern industry possible. Okay, so standardizing the motor itself was a huge step. But to actually produce millions of them for a rapidly growing world, the manufacturing process itself had to be completely revolutionized. Back in the day, highly skilled workers would wind every single copper coil by hand, and it was a real art form. But it was also incredibly tedious, it was inconsistent, and a teeny tiny mistake in the wire tension could cause a catastrophic electrical short. So the shift to automated winding machines was a genuine quantum leap, not just in speed, but maybe more importantly, in reliability. It was innovators and these companies who developed the super specialized machines that made this whole industrial transformation possible. They broke through the old production bottlenecks and supplied the entire industry with these amazing automated winders. And it wasn't just the winding. Even assembling the motor's iron core evolved. Instead of just manually stacking and securing these fragile steel plates, engineers came up with these clever automated techniques like cleating. And this process didn't just cut labor costs, it also made the finished motors a whole lot tougher. So just as industry was mastering this art of mass-producing reliable, standardized motors, a massive global conflict erupted. World War II would take all of this new industrial power and just push it to its absolute limits, accelerating technological development at a truly breakneck pace. All of a sudden, the stakes were literally life or death. A motor couldn't just work in a nice, temperature-controlled factory anymore. It had to perform flawlessly in the freezing altitudes of a B-17 bomber, or it had to withstand the bone-jarring shock of naval cannons. Failure was simply not an option. The really complex needs of combat aircraft forced a fundamental shift in thinking. See, early planes used pretty simple DC electrical systems, basically borrowed from cars. But the new heavy bombers, with their power-hungry gun turrets and landing gear, they had to transition to AC generators. They were smaller, they were lighter, and they packed an incredible power punch. The war also saw the first widespread use of a totally new breed of motor, the servo. Now, a standard motor it just spins. A servo, on the other hand, can move to an exact position and hold it there, using a feedback loop to make constant, lightning-fast adjustments. And these things weren't just for spinning fans. Oh no, servos were the key to automated accuracy. They were aiming massive searchlights, they were tracking enemy planes on radar, and they were laying huge naval guns on target with a speed and a precision that was just physically impossible for a human operator turning a crank. These battle-hardened innovations, they didn't just vanish when the war ended. They actually laid the groundwork for so much of the technology that powers our world today, everything from industrial robotics all the way to the autofocus in your camera. And maybe nowhere was electric power more vital than beneath the waves. Submarines, like the American Gatto class, used this brilliant hybrid system. On the surface, their diesel engines would just roar, but underwater, they'd switch to these massive, high-torque electric motors for silent, deadly running. The ability to just glide silently on electric power for up to 2 full days, that was a staggering strategic advantage. It was stealth, pure and simple, and it was all enabled by powerful and incredibly reliable electric motors. The entire industrial base mobilized for the war. I mean, companies that had pioneered motor controls in peacetime, like Ward Leonard, they completely converted their factories to produce nothing but components for warships, giving commanders the precise control they needed to maneuver these massive vessels in combat.
You know, electric motors are literally everywhere. They're the invisible workhorses of our entire world. But the motors we have today, they're miles ahead of the ones from the mid-20th century. Way more powerful, smaller, and a heck of a lot more reliable. So what on earth happened between the 1950s and the 1980s to cause such a leap? Well, it wasn't some flashy new discovery in physics. The real story is this relentless, behind-the-scenes engineering battle. Let's pull back the curtain on this unseen revolution.
So here's our game plan. We're going to dive into that unseen revolution by looking at 3 huge challenges that engineers had to solve. First, how to tame these things called parasitic currents. Then, how to conquer deadly heat. And finally, how to make these machines survive in the real, messy world. And at the end, we'll see what this all tells us about how technology really gets better.
You see, the big steps forward weren't glamorous at all. They weren't about rewriting the physics books. No, the real progress came from the super technical, slow and steady work of optimizing materials science, thermal management, and magnetic efficiency. This is a story about perfecting the boring stuff that, it turns out, changes everything.
To really get this revolution, first, we have to meet the villain of the story. Because inside every single AC motor, there was this hidden force at work, quietly stealing power and creating a massive, massive headache that engineers absolutely had to solve first.
And that energy thief has a name: eddy currents. These parasitic currents were a fundamental roadblock. If you wanted to make motors more efficient, more powerful, you first had to figure out how to fight a war inside the motor's own metal core.
So what in the world are eddy currents? Okay, imagine tiny, chaotic whirlpools of electricity just spinning around inside a solid chunk of metal when it's near a changing magnetic field. The problem is, these little whirlpools do zero useful work. They just spin around, generate a ton of waste heat, and actively suck power right out of the motor.
Okay, so how do they fix this? Well, the solution is just brilliant. On the left, you've got a solid iron core. It's basically an open swimming pool for these eddy currents to just go wild. But on the right, you see the genius solution. Instead of one solid block, the core is made of hundreds of paper-thin steel sheets, or laminations. Each one has this microscopic insulating layer. It's like putting up hundreds of tiny walls that stop those electrical whirlpools before they can even get started.
But they didn't stop there. The next big breakthrough was in metallurgy. By adding just a tiny bit of silicon to the iron, they created this amazing new alloy called silicon steel. What it did was fundamentally change the metal's properties. It drastically jacked up its electrical resistance, making it way harder for those parasitic currents to flow. It basically strangled them at the source.
From there, the industry perfected 2 special flavors of this steel. There's grain-oriented, or GO steel. Its magnetic properties are amazing, but only in one direction. Perfect for something stationary, like a transformer. But for a motor with its magnetic fields spinning around in a circle, you need something else entirely. And that's where non-oriented steel comes in. It has equal magnetic properties in all directions, which is absolutely essential for the spinning heart of an electric motor.
So, they managed to tame the energy thief inside the motor. But that victory created a brand new problem. When you make motors smaller and more powerful, they get hotter, and heat is the ultimate enemy. A motor's lifespan is basically dictated by one thing: how long its internal wire insulation can survive before it literally cooks itself to death.
And this timeline really shows how they won that war against heat. Early motors used natural stuff, cotton, paper, silk. It's what they had, but it just fell apart and turned to charcoal under heat. The real game changer was the invention of synthetic polymers and silicone resins. By the 50s and 60s, new standards like Class F and Class H insulation were common, which let motors run at temperatures that would have completely incinerated those older designs.
And just look at the incredible new arsenal of materials engineers suddenly had. We're talking about things like Mylar, that tough polyester film, and Nomex, a super heat-resistant paper. They even figured out how to create composites, sandwiching these materials together to get mind-blowing electrical insulation, flame resistance, and just plain toughness.
The importance of all this insulation tech is captured in the simple but super powerful piece of engineering wisdom. It's called the Rule of 10, and it's a principle that pretty much governs everything about how you design a reliable motor.
And here's the rule in action. Just let this sink in. A measly 10 degrees Celsius drop in how hot the motor runs doubles the life of its insulation. And the reverse is true too.
run at 10 degrees hotter, and you've just cut its life expectancy in half. You can see why engineers became absolutely obsessed with better insulation and better cooling.
All right, so now motors were more efficient, and they could handle their own heat. But then we started putting them everywhere, out of clean factories and into dusty farm fields, wet industrial sites, you name it. And a whole new challenge popped up. How do you protect the motor's sensitive guts from the outside world? This created a classic engineering dilemma, right? How do you get cooling air to all the hot parts inside, while at the same time sealing it all off from dust, rain, and grime? The answer led to two very different and very common ways to build a motor.
Let's break down this trade-off. On one side, you've got the open drip-proof or ODP motor. It's simple. It has vents that pull outside air directly over the hot bits inside. Super efficient for cooling, but, well, it's open, it's vulnerable. On the other side, you have the totally enclosed fan-cooled, or TEFC motor. This thing is completely sealed. It cools itself indirectly, with a fan on the outside that blows air over a bunch of cooling fins. It offers fantastic protection, but it's a compromise. It's heavier, pricier, and just a little bit less efficient at getting rid of heat.
So when you put it all together, the better steel, the advanced synthetic materials, the clever enclosure designs, you start to see the real story. There was no single eureka moment. The progress was the result of decades of these relentless, small, incremental improvements.
And this is the main takeaway. The unseen revolution that gave us the modern electric motor wasn't about reinventing the wheel. It was about the slow, hard, and brilliant mastery of these three fundamental areas of engineering. That's the boring stuff that powered the second half of the 20th century.
We're going to uncover how a massive global crisis lit the fuse for a technological revolution inside the humble electric motor. All right, let's rewind the clock to the 1960s. It was a time of some truly incredible innovation, and engineers were cooking up brilliant new motor designs. But every single one of them was hitting a brick wall, keeping them from really taking off. See, the standard motor at the time had this huge fundamental flaw. It used physical carbon brushes that were constantly scraping against a spinning ring to deliver power, and that meant friction, heat, electrical noise. They were literally chewing themselves up over time. But then in 1962, the brushless DC motor came along and flipped the whole design on its head. It put the magnets on the part that spins and used smart electronics to switch the power. No more friction, no more wear, just quiet, efficient power. It was a genius idea.
But here's the kicker. This amazing new brushless design, it was basically dead on arrival. Why? Because the magnets they had back in the 60s were just, well, they were pathetically weak. You couldn't create a strong enough magnetic field in a small space to make these motors useful. The idea was way ahead of its time. The materials just weren't there yet. Meanwhile, you had the undisputed king of all industry, the AC induction motor. And these things were, and still are, absolute workhorses. They're cheap, they're tough, they're super simple. But they had this one massive flaw. Their speed was literally chained to the frequency of the power grid. Here in North America, that's 60 hertz. The motor spun at one speed, and that was it.
So how did you control the speed of something like a giant industrial pump back then? Well, you did it in the clumsiest ways imaginable. You'd use these clunky mechanical gearboxes, or even worse, you'd run the motor at full blast and then just choke the flow with a valve. I want you to imagine driving your car with your foot slammed on the gas and using only the brake to control your speed. That's how much energy was just being burned off as useless heat.
For a long time, all this inefficiency wasn't seen as a crisis. It was just the cost of doing business. Until, of course, energy itself became the crisis. And in 1973, the world got hit with a shockwave.
In October of 1973, OPEC slammed the brakes on the world's oil supply with an embargo, and the fallout was immediate and it was catastrophic. Prices just exploded, the global economy went into a tailspin, and those images of endless gas lines became seared into everyone's memory. For the very first time, the entire world was forced to think about how much energy actually costs.
And I want you to understand the scale of the shock. We're not talking about a small price hike. The price of oil quadrupled, 4 times higher almost overnight. This wasn't a gentle change. It was a violent economic earthquake that changed everyone's priorities.
So this crisis sends governments and companies scrambling. They start doing these massive audits to figure out where is all of our energy actually going. They assumed the big culprits were cars and heating buildings, but then this famous 1976 report by Arthur D. Little came out, and it revealed something that was absolutely mind-blowing.
The answer was 64%. Let that sink in.
Nearly 2/3 of all the electricity in the United States was being consumed by electric motors. Not lights, not heat, but these hidden engines running our factories and our lives. And just like that inefficient AC motor wasn't just a small problem anymore. It was public enemy number one in the new war on energy waste. That one single number kicked off a frantic global race. The mission was crystal clear. If you could just make these motors a little more efficient, you could save a colossal amount of energy and money. So, the hunt was on. You know, the old way of thinking was really dug in. There was even this expert in London who stood up and claimed that you could only control an AC motor's speed with mechanical gears, period. But two engineers from a company called Danfoss, Arne Regier and Ara Jensen, they heard that and basically said, challenge accepted. They and a few others pioneered what we now call the variable frequency drive, or VFD. And the idea behind it is just pure genius. Here's how it works. First, you take that fixed 60 Hz AC power from the wall and you convert it into stable DC power. Then, with some really powerful electronics, you basically build a brand new perfect AC signal from scratch. And here's the magic trick. You can make that new signal any frequency you want, which gives you precise direct control over the motor's speed. And the results, they were absolutely staggering. I mean, look at this. The old way of just throttling the flow used 100% of the potential energy, but a VFD could slash that energy use by more than half, just by slowing the motor down to the speed you actually needed. It was a total game changer for industrial efficiency, and it was born directly out of this crisis. Okay, so while the VFD is busy solving the AC motor problem, that other brilliant idea, the brushless motor, was finally starting to get somewhere thanks to new samarium cobalt magnets. But then, guess what? It got hit with its own crisis. Political unrest in Zaire, which was the world's main source of cobalt, caused the price to just go through the roof. Once again, a great technology was being threatened by geopolitics. But you know what they say about necessity, right? This new cobalt crisis lit a fire under researchers to find an alternative. And in the early 80s, they found it, neodymium magnets. And these weren't just a substitute, they were a massive upgrade. They were way more powerful than the cobalt ones, and they didn't rely on such a volatile material. This was the breakthrough that finally unleashed the true power of the brushless motor. Now, at the exact same time all of this is happening with these powerful, efficient motors, a completely different revolution was taking off, the personal computer. And as it turns out, computers needed their own, very special kind of motor.
They needed what's called a stepper motor. See, unlike a normal motor that just spins and spins, a stepper motor moves in exact, perfect, repeatable little steps. You send it one digital pulse, it moves precisely one step. You send it 100 pulses, it moves exactly 100 steps. It was the perfect bridge between the digital world of ones and zeros and the physical world of movement.
And these little guys became the unsung heroes of the digital age. Every single time a floppy disk or a hard drive needed to move its little read/write head to just the right spot, a stepper motor did the job. Even the massive, incredibly complex machines that actually made the microchips relied on stepper motors to etch circuits smaller than a human hair. So you see how this all connects, right? The 1970s created this perfect storm. You had an energy crisis that was screaming for efficiency, and at the same time, a digital revolution that was demanding precision. And the result was this cascade of innovation that is still shaping our world today. Now, the really important thing to get here is that the core ideas, the brushless motor, the VFD, they already existed before the crisis hit. But it was the 1973 oil shock that acted as the ultimate catalyst. It created this immense economic pressure that fueled breakthroughs like the neodymium magnet and pushed things like VFDs into the mainstream. And get this, the pressure was so intense, it led to some really wild projects. In 1979, the oil giant Exxon, yes, Exxon, spent over $1 billion to buy an electric motor company to develop a hybrid car. And what was at the heart of their prototype? An advanced VFD, the very tech born from the desperate need to save energy. The project didn't end up going anywhere, but it just shows you how profoundly that crisis had shaken up the world. You know, when you think about what makes a modern electric motor so powerful, your mind probably jumps to the obvious stuff, right? The copper windings, the magnets, the raw physical muscle. But here's the thing. The real magic, the real revolution isn't in the brawn. It's in the hyper-intelligent brain that's controlling everything. It's a silent transformation in electronics and software that has, no exaggeration, changed everything.
I mean, if you were to pop the hood of an EV, what's the actual star of the show? It's not really the motor itself. In fact, a modern brushless motor is kind of helpless on its own. If you just hook it up to a battery, it'll just lock up, or maybe just hum uselessly. It needs a conductor, an orchestrator.
And this is where that whole brains versus brawn idea really clicks. The motor, that's the brawn. It's pure muscle. But the inverter, which is this amazing combination of power electronics and software, that's the brain. It's responsible for delivering a perfectly timed pulsating current that creates the magnetic fields and makes the motor spin with down to the microsecond precision. And it's this brain that has evolved way, way more dramatically than the motor's physical body.
Okay, so for the brain to get as smart as it is today, it had to clear a massive hurdle. And you're not going to believe this, but the problem was silicon. Yep, the same stuff that built the digital age was actually holding motors back. For a long time, it was a serious bottleneck.
For decades, this little guy, the silicon IGBT, was the undisputed king. It was the workhorse. Its whole job was to be an incredibly fast light switch, taking that smooth, steady DC power from a battery and chopping it up into thousands of little pulses every second. It was basically faking the AC current that the motor needed to run. But here's the catch with these silicon switches. They had a fundamental flaw. Every single time one of them flipped on or off, a tiny puff of energy was just wasted as heat. That's called switching loss. And even when it was just on, holding the gate open, it still leaked energy as heat. That's conduction loss. And when you're doing this thousands upon thousands of times every second, well, those tiny little heat leaks turn into a raging furnace. And I'm not exaggerating here, this wasn't just a minor issue. It got so bad that engineers were forced to build these huge, heavy, complex liquid cooling systems for one reason: to stop the inverter, the motor's brain, from literally melting itself. This put a hard, physical ceiling on how powerful and efficient early EVs could be. So, how'd they fix it? Well, the answer wasn't some clever new circuit design. It came from a fundamental breakthrough in materials science that just shattered the old limits. Enter silicon carbide, or SiC for short. Now, this stuff is what's known as a wide bandgap semiconductor. And you don't need a PhD to understand what that means. It's just tougher. Way, way tougher than silicon. Its bandgap is 3 times wider, its breakdown field is 10 times higher, it can handle way more electrical stress, and it runs happily at temperatures that would instantly fry a normal silicon chip. And get this, SiC isn't the only superstar on the scene. Think of SiC as the heavyweight champion for big stuff, like cars and industrial motors. But then you've got gallium nitride, or GaN, and it's like the nimble, lightning-fast welterweight champion. It's perfect for things that need crazy high switching speeds and have to be super compact, like drones, robotics, and all those tiny, powerful chargers we have now. But here's the thing, all this incredible new hardware, it's just powerful, dumb muscle. It's only half the battle. To really make it sing, you need a brain. And that meant a revolution had to happen in the code too. This is a really cool story. The solution is this mathematical masterpiece called field-oriented control, or FOC. And the idea has actually been around since the 70s, but back then computers just weren't powerful enough to run it in real time. The genius of it is that it lets a computer tame a wild, chaotic AC motor and control it as if it were a simple, predictable DC motor. Okay, stick with me here, because this is where the real magic happens. To get FOC, you have to picture 2 invisible forces inside the motor. First, there's quadrature force. This is the good stuff. It pushes perpendicular to the rotor's magnets and creates all the useful torque that actually spins the wheels. Then there's direct force. This is the bad guy. It pulls parallel to the magnets and does nothing but waste energy trying to stretch the motor apart. The entire goal of FOC is simple: max out the good force and crush the bad force down to 0. So how does it do it? Well, the FOC process is basically this lightning-fast mathematical dance that happens thousands of times a second. It measures the 3 chaotic AC currents coming in. Then, using these 2 clever mathematical tricks, the Clark and Park transforms, it translates all that chaos into a simple, stable viewpoint that's locked onto the spinning rotor. And from this new viewpoint, all that mess boils down to just 2 simple numbers: the good force and the bad force. The computer can then easily just crank up the good one, dial down the bad one, and then run all the math in reverse to create the absolute perfect electrical signal to send to the motor. It's genius.
Okay, so we've got revolutionary new materials for the hardware and this brilliant code for the software. So what? What does all this actually mean for you and me in the real world? This is where we see the payoff.
Let's kick things off with a number that's just mind-boggling. Some researchers in Switzerland figured out that if we only replaced the old silicon controllers in the world's industrial pumps with new silicon carbide ones, we could save 25 terawatt-hours of energy every single year. That's the kind of impact we're talking about from just one material in just one application. And you can see that jump right here. Old silicon systems, they were doing okay, maybe 85% efficient, but that means 15% of your precious battery power was just being blasted out as useless heat. Now, you combine that sick hardware with the FOC software, and total system efficiency skyrockets past 95%. Almost no energy is wasted.
And at the end of the day, all this invisible high-tech magic translates into real-world upgrades that you can actually see and feel. The inverters get way smaller and lighter. Our EVs get more range in that awesome instant torque from a dead stop. Drones can fly longer and hold steadier in the wind. And the motors themselves, they just run quieter and smoother than ever before.
Today, we're going to talk about the invisible engine that's completely changing the game for electric cars. And nope, it's not the battery, and it's not the motor. It's the code. We're going to see just how software is rewriting the rules of performance. I mean, it sounds like a trick question, right? How on earth can this huge chunk of metal and wires actually get better, get faster, without a single mechanic ever touching it? Well, that's the big mystery we're going to solve.
And here's the answer. The real hero in all of this, the thing that's making everything possible, isn't the hardware you can see. It's the computational power. It's the brain of the car. These tiny little microcontrollers that are basically running the whole show. And when I say running the show, I mean it. To just make the car go, these little chips are juggling an insane amount of work. They're precisely controlling magnetic fields, they're managing power to make sure nothing overheats, they're constantly looking for problems, and they're doing all of this at the exact same time, millions of times a second. It's nuts.
So what's doing all this heavy lifting? Well, it's these super powerful 32-bit processors designed specifically for cars. You're looking at chips from companies like Texas Instruments, Infineon, and ST Microelectronics. These are the specialized brains that have kicked off this whole software revolution on wheels. And all of this leads to what is maybe the coolest part for us as drivers. Your car gets better over time. It gets upgrades delivered right over the air, just like your smartphone. This quote just nails the shift in thinking. It used to be that the car you bought was, well, that was it. Its performance was locked in forever. But today, the personality of an electric motor can be totally changed, updated, and improved with a bit of new code. And this isn't just theory. Check this out. Tesla once pushed a software update that gave their cars up to 5% more driving range. They didn't touch the battery, didn't change a single wire. It was just smarter code telling the motor how to use electricity more efficiently. That's what we're talking about. Okay, so if that's what software can do, some companies are rebuilding the entire car around that idea. Let's take a look at Rivian, because what they did shows how a software-first approach can literally change the physical shape of a car. So, Rivian basically looked at the old way of doing things, with dozens of little electronic brains scattered all over the car, and said, nope. They pulled all of that complexity into just a few super powerful central controllers. It's like going from a messy spider web to a clean, simple nervous system.
So here's the before picture. A typical car had something like 17 of these separate little computers, all trying to talk to each other through a tangled mess of wires. It's complicated and it's heavy. By simplifying and centralizing the brains, Rivian was able to get rid of, get this, 1.6 miles of copper wiring from every single truck they build. That is just a staggering amount of complexity to just remove.
And all that wiring, it adds up. We're talking 44 pounds of dead weight that they just eliminated from the vehicle. Gone. And less weight means more efficiency and more range. A smarter car is literally a lighter car.
But okay, all of that is amazing, but maybe the most mind-bending thing that software can do is a trick that almost feels like it's cheating physics. It lets an electric motor spin way faster than it should be able to.
So let's start from a dead stop. You slam the accelerator.
the software immediately kicks into a mode called maximum torque per ampere, or MTPA. This is all about calculating the absolute perfect shot of current to give you that insane pin-you-to-the-seat acceleration, but to do it as efficiently as possible.
But there's a catch. As the motor spins up faster and faster, it starts to fight back. It generates its own electricity, creating this reverse pressure. You can think of it like an electrical headwind. It's called back EMF. And the faster you go, the harder that headwind pushes against you.
And eventually, you hit a wall. You get to a point where that electrical headwind pushing back is just as strong as the voltage from the battery pushing forward. That's the motor's base speed limit. At this point, you can't push any more power in, acceleration stops, it's a dead end. Or it should be. But here's the incredible software hack. The moment the car hits that limit, the computer does something that sounds totally backwards. It injects a tiny bit of negative current. This actually creates a magnetic field that fights and weakens the motor's own magnets. And by making the magnets weaker, that electrical headwind, the back EMF, suddenly drops way down. And now that the headwind is gone, the battery can push more power in again, and the car just smashes right through what should have been its physical top speed. Now, this isn't magic. It's just really, really clever physics being managed by software. The whole thing is a beautiful system of trade-offs, and the car's brain is making these decisions in real time. So you can think of it like the car has one motor that can operate in two totally different modes. At low speed, you're in MTPA mode for that crazy acceleration. But once you hit that speed limit, the software seamlessly switches over to field weakening. Now the trade-off is you lose a little bit of that peak torque, but what you gain is the ability to go much, much faster. And here's the huge payoff for this trick. Because software can so perfectly manage these two modes, it means that most electric cars don't need a heavy, complicated, multi-gear transmission like a gas-powered car. This one software technique literally simplifies the entire design of the automobile. How in the world do you fit over 700 horsepower? We're talking more than a Lamborghini Huracan inside a suitcase you could carry onto an airplane. I mean, it sounds completely impossible, right? Well, it's not. That is the staggering power density modern EV motors have achieved, and we're going to break down exactly how engineers pulled it off. So let's start at the beginning. You know, Tesla really kicked off the modern EV era, but the motors in their first game-changing cars, like the Model S, they had a pretty significant hidden flaw. See, those early Teslas used something called an induction motor. It's a design that's actually remarkably similar to the original patents from the late 1800s. And they're brilliant, really. They're super durable, and importantly, they don't need any of those rare earth permanent magnets. The magnetic field from the stationary part, the stator, cleverly induces a current in the spinning part, the rotor. Voila, you get magnetism and rotation. But, and this is a big but, there's a catch. This whole induction process has a fatal, unavoidable thermodynamic flaw. It wastes up to 4% of the car's precious battery energy just to keep that magnetic field alive. Now, 4% might not sound like a lot, but when every single mile of range matters, that's a huge problem, especially when you're just cruising on the highway. So to fix this, when Tesla was designing the car for the masses, the Model 3, they knew they had to squeeze out every possible mile of range, and their solution was to ditch their namesake induction tech for something totally new, something revolutionary. They came up with this, the interior permanent magnet synchronous reluctance motor. Yeah, I know, it's a mouthful, but this complex hybrid thing has become the absolute gold standard for pretty much every high-performance EV out there. It's a true masterclass in modern magnetic engineering. So how's it built? Well, instead of just slapping magnets on the outside where they could fly off at high speed, engineers cut these really complex asymmetrical grooves deep into the iron rotor. Then they bury these super powerful razor-thin permanent magnets inside those grooves. And for the really insane versions, like in a Model S Plaid, the whole rotor is then wrapped in a carbon fiber sleeve just to stop it from literally exploding from the centrifugal force at over 20,000 RPM. Now, the real genius here is that this design uses two different types of force at the exact same time. First, you've got the simple magnetic pull on those magnets buried inside. But then you also get something called reluctance torque. Okay, think of a magnetic field like it's water. It always wants to take the path of least resistance. The motor's computer pulses the electromagnets, and the shaped iron parts of the rotor just snap into alignment, following that easy path. It's an incredibly efficient 1-2 punch of forces. Okay, so once this new hybrid motor became the standard, the engineering arms race shifted. The next big battle was all about optimization. The question became, how do we squeeze even more power out of the exact same amount of space. And the problem was hiding in the windings. For ages, motors were wound with hundreds of little round copper wires. But here's the thing about geometry. You can't pack circles into a square slot perfectly. This led to a really poor slot fill factor. Look at that. Over half the space was just wasted air. And since air doesn't conduct electricity, all that space was doing absolutely nothing.
The solution? Hairpin windings. This was a game changer. Instead of flimsy round wires, engineers started using solid rectangular copper bars shaped kind of like hairpins. Robots insert them and they lock together perfectly, just like puzzle pieces. And look at that jump. The amount of copper you can pack in skyrockets to 80%.
And here's why that's so crucial. More copper means less electrical resistance. Less resistance means higher efficiency and way more power. This single innovation is what pushed power density from around 3.5 kilowatts per kilogram up to 4.5. You're literally getting more horsepower for the same weight. But of course, when you cram all that electrical energy into such a tiny, dense package, you create a brand new, massive problem, a truly terrifying amount of heat. This meant engineers needed an equally clever leap in cooling tech just to stop the motor from melting itself into a puddle. And this is where a company like Lucid Motors really flexed its engineering muscles. Instead of a normal water jacket around the outside, they invented this patented microjet system. They machined these tiny, microscopic fluid channels right into the stator itself, so transmission fluid can flow right next to the hottest parts. Then, that fluid gets violently sprayed in a high-pressure jet directly onto the copper ends, just ripping the heat away. It's an incredibly aggressive and incredibly effective way to cool things down.
So, with power and cooling getting figured out, engineers started to ask an even crazier question. What if we've been using the wrong shape this whole time? And that led to some really radical new designs that threw out a century of convention.
First up was the jump to high-voltage systems. Most early EVs ran at 400 volts, but companies like Porsche and Lucid pushed their systems to over 900 volts. Why does that matter? Well, basic physics. Power equals voltage times current. So if you more than double the voltage, you can get the same amount of power with less than half the current. And less current means you can use way thinner, lighter copper wires, which saves a ton of weight and cuts down on heat.
But the most radical shift was in the actual geometry. For 100 years, almost every motor was a radial flux design, basically a cylinder spinning inside a bigger cylinder. Now, look at this new axial flux motor. It's shaped like a pancake. The physics here are an absolute game changer. In a normal motor, torque scales with the square of its diameter, but in this pancake motor, it scales with the cube of its diameter. That huge geometric advantage means it can be up to 50% lighter while kicking out 4 times the torque. It's no surprise Mercedes-AMG bought the company making these to power their next generation of supercars.
So all these hardware innovations created motors with just unbelievable potential. But to truly unlock it all, that required the final and most profound leap yet, moving from steel to software. The new frontier is all about using flawless code to do things mechanical parts could only dream of. And that brings us to torque vectoring. Instead of having one big motor driving the wheels through a heavy, clunky mechanical differential, companies like Rivian and Rimac just put a separate, independent motor on each wheel. This lets a central computer control the exact amount of power going to each individual tire hundreds of times every second, with absolute surgical precision. And the ultimate expression of this software-first approach? Well, that would be the Rimac Nevera, a car that, by the old rules of mechanical engineering, simply shouldn't exist. The Rimac Nevera makes a grand total of 1,914 horsepower. Yeah, that power comes from 4 custom-built permanent magnet motors, all orchestrated by one of the most sophisticated pieces of software on the planet. I mean, these numbers are just mind-bending. 0 to 100 kilometers an hour in 1.81 seconds. It broke 23 performance records in a single day. But what's truly physics-defying is the handling. The software literally forces the car to pivot through a corner like a fighter jet, managing the power at each wheel to achieve a rotation that no mechanical all-wheel drive system could ever match.
All right, let's get right into it. You know, while we were all watching the electric car boom, something really wild was happening in the skies, kind of under the radar. It all started with these tiny acrobatic hobby drones, but now, that exact same technology is literally powering the next generation of human flight. So today, we're going to unpack exactly how that happened.
First question you have to ask is, if you've ever seen a modern racing drone video online, you've seen them flip, dive, and just stop on a dime. And you've got to wonder, how in the world is that even possible? It looks like it's breaking the laws of physics. Well, I'm here to tell you it's not magic. It's this perfect combination of some very specific hardware and some ridiculously clever software.
So here's our game plan. We're going to start with the drone revolution itself. Then we'll zoom right in on the nitty-gritty, the hardware and the software that makes it all tick. And from there, we're going to zoom way out and see how these same ideas are being scaled up for human transport. And finally, we'll take a peek at what's just over the electric horizon.
To really get this, you have to understand that the people building car engines and the people building drone motors were playing two completely different games. They were trying to solve two totally separate problems.
And this right here is the key. Car engines, for decades, have been engineered for sustained efficiency. Think cruising on the highway. Drone motors, though, they were built for one thing and one thing only: raw, instantaneous power. We're talking about the need to react in microseconds, with the absolute highest thrust possible for the lowest weight imaginable. And that required a whole new way of thinking about motor design.
So let's talk about that hardware. Let's get into the anatomy of what makes these things so agile. At the absolute heart of every single one of these high-performance drones is a very special type of motor.
It's called an outrunner motor. Now, in a normal motor, the shaft in the middle spins, right? While with an outrunner, it's flipped inside out. The center part with the copper windings stays completely still, and the entire outer bell, which is lined with powerful magnets, is what spins around it. This design gives it just incredible torque, basically leverage, letting a tiny little motor swing a big, aggressive propeller with a ton of force.
And if you're talking about these motors, the most important number is the kV rating. It's actually pretty simple. It just tells you how many RPMs the motor is going to try to spin for every single volt of electricity you push through it. So a higher kV means you get a higher top speed, while a lower kV usually means more grunt, more torque for spinning bigger props.
Things have gotten so specialized that even the sizes are standardized. So if you hear a drone pilot talking about their 2207 motors, they're not just saying random numbers. They mean the stator, that's the stationary part inside, is exactly 22 millimeters wide and 7 millimeters tall. And that specific size has become the gold standard for 5-inch racing drones because it just hits that perfect sweet spot between raw torque and lightning-fast RPM changes.
Okay, but here's the real kicker. As crucial as all that hardware is, the thing that truly changed the game wasn't the metal. It was the code. The real revolution was happening in the microscopic lines of software that tell those motors exactly what to do.
And that job belongs to the Electronic Speed Controller, or ESC. The best way to think of it is as a translator. It sits between the drone's brain, the flight controller, and its muscles, the motors. It takes these abstract digital commands like go faster or stop now, and turns them into physical rotation, and it has to do it in thousandths of a second. And the evolution of the software on these little ESCs happened at a breakneck pace. I mean, in the early days, we were using these slow, kind of sloppy analog signals. Then custom firmware like Simon K came along and just blew the doors off response times. But the real game changer was something called BL Heli, which introduced active braking, the ability for the ESC to literally slam on the brakes and stop a prop instantly. And that all led us to the modern era, with 32-bit processors running protocols like D-Shot, which got rid of the messy analog signals entirely in favor of perfect, high-speed digital data.
Here's a way to think about it. The old analog system was like trying to shout directions to someone across a crowded, noisy room during a storm. The message is slow, it gets distorted, it's just not reliable. Digital D-Shot, on the other hand, is like sending a perfect, crystal-clear text message. It's an absolute, incorruptible packet of data that arrives instantly and is perfectly understood. It's all about precision and speed.
But wait, it gets even better. The latest and greatest version, called bidirectional D-Shot, creates a constant two-way conversation. So the flight controller tells the motor, spin this fast, and the motor immediately reports back its exact RPM thousands of times every second. This feedback loop, this is the secret sauce. The drone can literally feel its own vibrations from the motors and mathematically cancel them out in real time. And that is how you get that impossibly smooth, locked-in flight you see in pro videos.
Okay, so that's the micro-level deep dive. Now let's pull the camera way, way back. Because these exact same principles,
Super powerful electric motors, ultra-fast digital control, and building in tons of redundancy, these are the absolute foundation of the brand new electric vertical takeoff and landing industry. You know, the eVTOLs, or flying cars we keep hearing about.
The core idea here is called distributed electric propulsion. So, instead of a classic helicopter that has one giant, incredibly complex engine where one failure can be catastrophic, eVTOLs spread the workload across lots of smaller, independent electric motors. And this isn't just about making it fly. It's a complete reimagining of what safety in the air looks like.
So let's take the Joby S4 for example. It's one of the front runners in this whole air taxi space. It uses 6 big, articulating prop rotors. So right off the bat, you've got layers of redundancy that a single rotor helicopter just can't dream of.
But here, and this is where it gets really brilliant, each one of those 6 big units isn't just powered by one motor. Nope, it's driven by 2 completely independent motors with their own separate windings. That means if an entire battery system or motor controller goes down, the second motor can instantly take the full load, no problem, allowing the aircraft to keep flying and land safely. It's literally redundancy on top of redundancy.
And this isn't some one-off design either. Look at the Archer Midnight aircraft. It takes a very similar approach, using a whopping 12 separate electric motors. If one of those fails, its software, in an instant, adjusts the power and the blade pitch on the other 11 motors to maintain perfect, unshakable stability. That's a level of digital balancing that's just physically impossible with old-school combustion engines.
So you can see, different companies are taking slightly different angles here. You've got Joby and Archer laser-focused on all-electric air taxis for getting around cities. But then you have companies like Mightyfly who are tackling a whole different beast, long-range cargo. And that requires a very different solution.
And that brings us to the single biggest challenge for electric aviation, and that's range. Batteries, as you know, are incredibly heavy. So what does the future actually look like when you need to fly for longer distances?
Mightyfly's answer for its 600-mile cargo drone is a hybrid system. So it uses 8 powerful electric fans for that super quiet and efficient vertical takeoff. But once it's up and flying like a plane, a small, efficient combustion generator kicks in, not to power the props, but to recharge the batteries in the middle of the flight. This is what allows it to do these long, multi-stop delivery routes without having to land for hours to recharge.
And please, don't make the mistake of thinking this is just for little drones or futuristic air taxis. This technology is scaling up to traditional airplanes as we speak. Companies like Magniex are building megawatt-class electric motors. Look at this Magni 650. This monster puts out 700 kilowatts of power, and it's specifically designed to retrofit existing commuter airplanes. The main takeaway here is that this is not some far-off fantasy. It is actively going through rigorous FAA certification testing right now.
You know, the big switch to electric vehicles feels like this huge, undeniable win for the planet. And in a lot of ways, it is. But here's the thing. Behind that clean green image, there's a serious bottleneck. A crisis, really. And it turns out the special materials that make these cars so amazing have become a massive liability. It's hiding in plain sight, right inside the motor. So what is the secret? This hidden crisis that could actually stop the whole EV revolution in its tracks? Well, to find the answer, you have to look deep inside the heart of the machine itself. And it all comes down to this. The magnet bottleneck. We're talking about the incredibly powerful, super compact permanent magnets that give modern electric cars their incredible punch and efficiency. Now, these are not your average refrigerator magnets, not even close. They are technological marvels, and they're made from some very, very special ingredients. So what are these special ingredients? They're called rare earth elements. And right away, that name is, well, it's kind of misleading. These metals aren't actually that rare in the Earth's crust. The real problem, the absolute crisis, isn't about finding them. It's that turning them from rocks into pure, usable metals is a complete environmental nightmare. It's just devastatingly difficult and dirty. And because it's such a tough process, something really dangerous has happened with the supply chain. I mean, look at these numbers. It's staggering. China processes 95% of the world's supply. That's not just a lead, it's a chokehold. It creates this massive vulnerability for basically every other country on Earth. And look, this isn't just about politics or supply chains. The environmental cost of having this one dirty process concentrated in one place is, wow, it's absolutely staggering. And it kind of makes you question how green this green technology really is. Okay, just look at this number. 2,000 tons. What is that? Well, for every single ton of usable rare earth metal you get, you create 2,000 tons of toxic waste. Just let that sink in for a second. The ratio is insane.
And we're talking about some seriously nasty stuff here. A cocktail of toxic chemicals and even radioactive materials like thorium. It all gets dumped into these enormous, leaky waste ponds. I mean, one source describes them as brimming with thick, black, toxic sludge. You can just picture it. And this toxic gump seeps into the groundwater, it ruins farmland, and it has caused these horrifying health crises in what people have started calling cancer villages.
So you've got this environmental catastrophe on one hand, but then there's the other side of this coin. This supply chain dominance has been turned into a very powerful political weapon.
And this isn't some theoretical threat. We've already seen it happen. Back in 2010, China decided to just turn off the tap. They slapped on these huge export quotas. The result? Total chaos. Prices for some of these metals shot up by more than 900% in less than a year. It sent a massive wave of panic through the auto industry, the defense industry, pretty much everyone.
And guess what? That threat is even bigger today. Right now, the West's most vital technologies are almost completely dependent on one single supplier who keeps tightening the screws with new export controls. So you can see why this is a 5-alarm fire for engineers. The choice is stark: innovate or risk total collapse.
Okay, so that's the bad news. A lot of it. But here's where the story gets really, really cool. This massive pressure is forcing some incredible innovation. And the first line of attack is a full-on recycling revolution, figuring out how to reclaim these precious metals from the mountains of old electronics we already have. One of the coolest new tricks is a process called HPMS. See, getting these tiny, powerful magnets out of old motors used to be a huge pain, almost impossible. But with this new technique, they just expose the old motor parts to hydrogen gas. And the hydrogen does something amazing. It goes right for the magnet material, makes it swell up, and then it just crumbles into a fine powder. A demagnetized powder that's super easy to collect and reuse, infinitely.
Recycling is great. It's a huge step. But the really radical solution? It's to reinvent the motor itself, to basically design the problem away. The thinking here is, what if this isn't a materials problem at all? What if it's a software and engineering problem?
So this has kicked off a brand new competition in motor design. You've got the old champ, the permanent magnet motor. It's powerful, but totally dependent on rare earths. And now you've got two new challengers stepping into the ring, both completely magnet-free: the switched reluctance motor and the externally excited motor.
All right, first up is the switched reluctance motor. The design is almost ridiculously simple. The part that spins, the rotor, it's basically just a chunk of steel with some teeth cut into it. That's it. The motor works by firing electromagnets on and off really, really fast, which yanks those steel teeth around, making it spin. The problem has always been that this process is loud and really shaky. But this is where brilliant software comes in and saves the day. Modern computer chips are so fast, they can shape and time the electrical pulses with unbelievable precision. It's like putting noise-canceling headphones on the motor. The software sends these tiny, perfectly timed counterpulses that smooth out all the vibrations before they even happen. And suddenly, this simple, clunky design becomes silent, smooth, and just as efficient as its rare earth rivals. It's a total win for clever code over rare materials.
Okay, so the second magnet-free approach tackles a totally different engineering puzzle. The idea is, instead of permanent magnets on the spinning rotor, you just wrap it in copper coils to make an electromagnet. Simple enough, right? But wait, how do you get electricity into something that's spinning thousands of times a minute without any physical wires touching it? The answer is just, it's beautiful. It's basically wireless charging. You know, just like the charger for your phone, they built a tiny, powerful version of that right inside the motor. It beams electricity across the air gap from the stationary part to the spinning part. No wires, no contact. It's genius.
And this contactless design is a complete game changer. There are no brushes to wear out, it needs 0 rare earth metals, and it hits a benchmark efficiency of 95%. But maybe the coolest part is that it gives the car's computer total instantaneous control over the motor's magnetic field, optimizing performance every single millisecond. It's proof that you don't need a geopolitical dependency to get world-class performance. And really, that's the big takeaway from all of this. When we're backed into a corner by a huge, seemingly impossible problem, whether it's environmental, economic, or political, we don't just give out. We innovate our way out. The future of propulsion isn't about digging more stuff out of the ground. It's about what we can build with our own ingenuity.
Let's talk about arguably the most transformative device ever created, one that's the absolute foundation of our modern lives. You know, from our cars to our factories, the electric motor is the unseen workhorse of the world. But today, it's going through a massive revolution. It's evolving from a 19th century marvel into the hyper-intelligent heart of the 21st century. So where did this all begin? Well, the motor's journey really kicked off way back in 1821 with Michael Faraday's discovery of electromagnetic rotation, which was basically just a spinning wire in a cup of mercury. Kind of simple, right? But over the next 100 years or so, it became the industrial workhorse, replacing steam and manual labor everywhere. Today, though, the landscape is completely different. These motors have become the algorithmically driven core of our world.
And this whole transformation, it really starts with how motors are even dreamed up in the first place. We're now in an era where artificial intelligence isn't just some tool in a toolbox. It's a co-creator, totally reinventing the design process from the ground up.
Think about it. For over 200 years, motors have been designed by human engineers. And what that meant was they were symmetrical, they made sense to us, they followed rules we could visualize and, build by hand. But that whole approach, it was starting to hit a hard physical wall in terms of how efficient it could get. Okay, this is where things get a little wild. We're now using what are called physics-based diffusion models. Basically, it's AI that actually understands the laws of physics. So engineers can now just input what they need, their performance goals, and the AI then generates hundreds of these, well, frankly, bizarre and asymmetrical designs. I mean, these are shapes and geometries a human engineer would simply never come up with, but they are radically more efficient. So here's the crucial point. It's this human-AI co-creation process. You feed the AI the constraints, the torque you need, the heat limits, the efficiency targets, and it spits out these perfectly optimized geometries for the rotor, that's the spinning part, and the stator, the stationary part. This just massively accelerates prototyping and lets you squeeze every last drop of electromagnetic performance out of simple iron and copper. All right, so let's shift gears from design to the materials themselves. We're going to see how revolutionary new magnet is solving not just an engineering problem, but a huge geopolitical one too. The breakthrough material is called iron nitride, and this is a big deal. It's the first truly viable high-strength alternative to rare earth magnets, which for a long time have been dominated by a single supply chain. Companies like Niron Magnetics are pioneering this material, and get this, it's made from two of the most abundant elements on Earth, iron and nitrogen. And when you put them side by side, the comparison is just stark. On one side, you've got your rare earth magnets. They rely on these geopolitically concentrated and environmentally costly elements. But on the other side, you have iron nitride, abundant, sustainable, and totally conflict-free. This is an absolute game changer for building resilient supply chains. And the performance boost? It's huge. Because of its unique physical properties, engineers can pair iron nitride with these advanced variable flux motors. Now, these are really cool. They're motors where the magnetic field can be adjusted on the fly by software. And what that does is boost EV efficiency at highway speeds by a staggering 20 to 30%. But let's look even further ahead, beyond our cars and into the sky. Here we get to the absolute pinnacle of electric propulsion physics, superconductivity. I mean, this is one of the biggest challenges for decarbonization, right? To electrify a huge passenger jet, you need multi-megawatt motors. But a traditional copper motor, powerful enough to do that, would be so heavy, the plane literally couldn't even take off. It's a fundamental physics barrier we've been stuck on. The answer, it turns out, lies in this almost miraculous quantum property. When you cool certain materials down to incredibly low temperatures, their electrical resistance just vanishes. It drops to absolute zero. And the effect is just transformative. By cooling these advanced wires, all that resistance just disappears. This lets them carry massive electrical currents with zero energy loss to heat. That unlocks immense magnetic fields and unbelievable power from a tiny, lightweight package. This is exactly the kind of power density aviation has been desperate for. So this has always been the showstopper, right? I mean, keeping something at cryogenic temperatures outside of a lab, let alone on a flying airplane, it seems almost impossible. You'd think the cooling equipment would be way too heavy and complex. But some truly brilliant solutions are finally emerging. It turns out engineers are chasing two main paths to solve this.
The first, coming from firms like Kinetics, is to basically build tiny, hyper-efficient refrigerators directly into the motor's spinning rotor shaft. The second idea is, well, even more ingenious. The plan is to use the plane's own liquid hydrogen fuel, which is already stored at a frigid -253 degrees Celsius, as a built-in heatsink to keep the motor in its superconducting state. A brilliant two-for-one solution.
And the result of all this? You get a motor with operational efficiencies exceeding 99%. Now, this isn't just a small step up. This is a monumental leap. It's widely considered the only realistic engineering path to get to fully electrified commercial jumbo jets.
So let's bring this all together for a second. We've gone from AI-generated geometries and sustainable magnets all the way to the quantum magic of superconductivity. The humble electric motor is being completely reborn before our very eyes. It's really an incredible story arc. What started as just a simple copper wire spinning in a lab has now completed its 2-century journey. It's no longer just a workhorse. It is the quantum-cooled, software-defined engine that is going to power our future.